Welcome, everyone. Today, we are exploring a critical component of architecting AI-powered business solutions, reviewing data for grounding. Let's get started. Welcome to this training on analyzing requirements for AI-powered business solutions. Today, our main focus is going to be on a concept called grounding, and specifically, how we review data for grounding. What exactly is grounding? In simple terms, it ensures that your AI agent responds using trusted, domain-specific organizational data rather than its own internal training data. This is the absolute foundation of reliable AI. Why do we do this? Because without grounding, language models can guess or hallucinate, providing confidently incorrect answers. How does it work? Platforms like Microsoft Copilot use a retrieval API and semantic indexing to map your enterprise content and feed it to the AI as context. But remember, the AI is only as good as the data it's fed. That's why we must deeply analyze 5 core dimensions of our data: accuracy, relevance, timeliness, cleanliness, and availability. Over the next several slides, we will deep dive into each of these dimensions. Let's turn our attention to the flowchart on the screen, which illustrates the core architecture of an AI grounding process. On the left, we start with the user query. This flows directly into our AI agent. Now, rather than just guessing the answer, notice the critical pathway pointing to the retrieval API and down to grounding data. The agent retrieves specific, trusted information from this repository. From there, the data flows through our evaluation filters: accuracy, relevance, timeliness, cleanliness, and availability. Only data that successfully passes these strict quality dimensions is allowed to proceed. Finally, this filtered, high-quality context is fed back into the generative model, resulting in the final node on the right, a trusted response. This diagram visually emphasizes that the quality of the final output is completely dependent on the rigorous filtering of the underlying organizational data. Now let's explore our first key dimension: accuracy. What exactly do we mean by accuracy in the context of AI grounding? Accuracy means your data reflects real, verifiable facts. It is the absolute baseline for any business solution. Why is this critical? Because if you feed an AI inaccurate content, it will confidently generate incorrect or harmful outputs, leading to an immediate loss of trust from your users. How do we achieve this? We must ensure data is verified by subject matter experts, or SMEs. We must match the data to authoritative sources within the organization, keeping it completely free from errors or outdated assumptions. As a deep dive, consider the phenomenon of hallucination. AI models are designed to predict the next word. They don't inherently know truth from fiction. By restricting the AI's knowledge base strictly to SME-verified, highly accurate data, we artificially bound the model's universe of facts. This transforms the AI into a reliable business assistant. Let's walk through this process diagram to see how accuracy is enforced operationally. We start at the top with raw enterprise data. This represents the unfiltered documents, emails, and files scattered across an organization. Before this data ever reaches the AI, it flows into a critical decision gateway, the SME verification node. This represents the human-in-the-loop or automated verification process. If the data is outdated or incorrect, it follows the rejected path to be flagged for correction. However, if the SME verifies the facts, it follows the approved path into the authoritative data store. It is exclusively from this heavily vetted store that the AI semantic index is built, leading to accurate AI output. By visually isolating the AI model from the raw, unverified data, this flowchart clearly demonstrates that accuracy isn't just a characteristic of the data, it is a strict architectural boundary we must build into our solutions. Moving on to our second dimension: relevance. While accuracy ensures the data is true, relevance ensures the data perfectly matches the intended use case or user intent. Why is this distinction important? Because modern AI uses semantic search, which looks for meaning rather than just keyword matches. If data is irrelevant, semantic search might retrieve conceptually similar but contextually completely wrong content. For example, an HR bot shouldn't pull from IT manuals just because both use the word policy. How do we guarantee relevance? We must apply strong metadata tagging, effective chunking strategies, and strict data boundaries to filter content by its specific business domain. In a deep dive scenario, remember that language models have a limited context window. If we fill that window with irrelevant noise, the AI loses focus on the actual user prompt. High relevance keeps the AI laser-focused on the exact workflow at hand, driving much higher quality responses. If you look at the diagram on your screen, you will see a visual representation of how relevance impacts AI outputs. On the left, we have a specific user intent, asking about an HR policy. This query hits the semantic search engine. Now, notice the two diverging paths. The solid line leads to HR document A, which represents highly relevant context and ultimately leads to a precise answer. The dotted line, however, points to IT document B. Even though it might share similar vocabulary, it acts as contextual noise. If this irrelevant document is fed to the AI, it degrades the quality of the response. This diagram highlights why solution architects must build strict scoping and metadata rules into their semantic search engines. We must actively prune the dotted pathways of contextual noise so that the AI only receives data that is strictly relevant to the user's specific business process. Our third critical dimension is timeliness. Timeliness guarantees that the grounding data is current and reflects the absolute latest state of the organization. Why does this matter? Because business moves fast. If your AI is grounded on last year's travel policy, the outputs degrade rapidly. Employees might act on obsolete procedures, introducing massive operational and compliance risks. How do we manage timeliness? We have to ensure that our semantic indexes are continuously updating. This involves tracking modified dates and establishing strict, automated data refresh schedules. Let's do a deep dive here. Timeliness isn't just about adding new data, it's equally about removing the old. Solution architects must design synchronization jobs that not only ingest fresh content from SharePoint or OneDrive, but also purge deleted or deprecated content from the AI's memory. If stale data remains in the index, the AI might still retrieve it, completely undermining the trust in the system. Let's explore this timeline diagram, which maps the lifecycle of timeliness. At the top, we have a trigger event, content updated by user. This instantly kicks off an automated sync job. The system then hits the timestamp validation node. Here, the architecture makes a crucial decision. If the content is new or current, it flows to the left, updating the semantic index with fresh vectors. If the content has been marked as stale, deprecated, or deleted, it flows to the right, where it is actively purged from the index. Both of these actions, updating the new and purging the old, converge at the bottom to create a consistently up-to-date AI agent. This flow demonstrates that timeliness is an active, ongoing architectural requirement. You cannot simply upload data once and walk away. The system must continuously prune and refresh itself to maintain operational integrity. Dimension number 4 is cleanliness. When we talk about cleanliness, we mean that the data is well-structured, standardized, and entirely free of noise, what we call data pollution. The basics of clean data include clear document structures, absolute elimination of duplicates, and stable, predictable formatting. Why do we care so much about formatting? Because data pollution actively degrades the reliability of AI systems. When you feed messy data into an embedding model, it creates poor, fuzzy vectors, which lowers retrieval precision. How do we fix this? We must normalize and structure our data before ingestion. We need to eliminate scattered data silos and enforce enterprise taxonomies. Let's look deeper. Imagine a massive corpus of old emails. If they are full of HTML tags, boilerplate signatures, and endless reply chains, the AI struggles to find the actual knowledge. Architects must build pre-processing pipelines to scrub and clean this text before the AI ever sees it. This diagram perfectly illustrates the journey from chaos to clarity. Starting on the left, we have messy raw data, the typical state of enterprise files. This data is fed into a pre-processing pipeline. The first action inside this pipeline is to remove duplicates and HTML, stripping away the digital noise. Next, the data moves to standardized taxonomy, where naming conventions and metadata are aligned to enterprise rules. This results in clean text chunks. Because these chunks are pure, focused information, they generate high-precision vector embeddings in the final step. This visual makes it clear that you cannot bypass the cleaning phase. If you put messy data directly into a vector database, you get messy, unreliable AI outputs. Cleanliness is a mandatory transformation step that converts human-readable documents into mathematically precise AI assets. Our final grounding dimension is availability. In the AI world, availability doesn't just mean system uptime. It means the data is accessible and indexable strictly according to user permissions. The basic rule is this: AI agents can only ground responses using data that the specific requesting user already has access to. Why is this so crucial? Because if an AI bypasses security trimming, it could expose sensitive financial or HR data to unauthorized employees, causing massive security breaches. How do we enforce this? We leverage tools like the Copilot Retrieval API and Microsoft Graph, which are fundamentally designed to respect your existing Microsoft 365 role-based access controls. Taking a deep dive into architecture, true availability requires a zero-trust mindset. We must enforce the principle of least privilege, rigorously apply Microsoft Purview sensitivity labels, and establish data loss prevention boundaries so the AI acts as a secure, compliant participant in your ecosystem. Let's trace the security flow in this diagram to understand availability in action. At the top, a user asks a question. Immediately, the request hits a strict gateway, the Identity and Access Check node. The AI system evaluates who the user is and what they're allowed to see. If the user does not have permission to view the underlying documents, the system takes the right-hand path to block data retrieval, resulting in an access denied message. Crucially, the AI is not allowed to summarize data the user can't see. However, if the user is authorized, the flow moves down the left path to retrieve allowed M365 data. Only then does the system generate a safe response. This flowchart reinforces that availability is synonymous with security. The AI agent acts as a secure proxy, completely bound by the organizational identity and access management rules you have already established. Now that we understand the 5 dimensions of grounding data, how do we actually build this into a solution? We do this by designing a robust data processing workflow. What is this? It's a structured pipeline covering ingestion, preparation, indexing, and retrieval. Basically, it's the engine that moves data from raw storage into an AI-ready state. Why do we need a complex pipeline? Because a well-architected pipeline balances performance, cost, and governance, transitioning your AI from a fragile prototype into a trustworthy production system. How is it done? By applying semantic chunking, breaking documents into logical pieces, generating vector embeddings, and building hybrid search indexes that combine keyword and semantic search. Diving deeper into the architecture, this is what we call a RAG pipeline, or Retrieval Augmented Generation. RAG handles the heavy lifting of cleaning and orchestrating the data so that by the time the prompt reaches the large language model, the context is absolutely perfect. Take a look at the data pipeline diagram on your screen. This represents the full lifecycle of grounding data processing. On the far left, we begin with data ingestion, pulling from our secure sources. Next, we apply the cleanliness dimension in the cleaning and normalization node. Once clean, the text undergoes semantic chunking, breaking it into sizes the AI can digest efficiently. Those chunks are then converted into math via vector embeddings. These vectors are stored in a hybrid search index, which guarantees our accuracy and relevance dimensions are easily searchable. Finally, this culminates in RAG orchestration on the right, where the AI dynamically retrieves this perfect context to answer a user's prompt. This linear flow proves that high-quality AI responses are not magic. They are the result of a highly disciplined, multi-stage data engineering pipeline. In our final slide, we must address governance and continuous review. What is this? It is the ongoing operational model required to maintain data quality and compliance long after the AI goes live. The basics involve establishing an AI center of excellence and assigning strict accountability to data owners and stewards. Why is this a mandatory step? Because enterprise data is alive, it changes, and models experience drift. Without continuous governance, an AI that was perfectly accurate on day 1 will become unreliable by day 90. How do we prevent this? We implement rich telemetry monitoring, conduct regular permission audits, and set up automated alerts for anomalies or guardrail violations. Taking a deep dive, true governance means applying application lifecycle management ALM to your data itself. You must build promotion gates. Just like software code, your grounding datasets must pass strict quality, lineage, and safety checks in a test environment before they are ever allowed to touch your production AI systems. Let's conclude by examining this continuous governance feedback loop. Starting at the top left, the system actively works to monitor telemetry and logs. It constantly asks the critical question in our decision node: detect data drift. If everything is operating smoothly and no drift is detected, the system simply loops back to continuous monitoring. However, if data staleness or inaccuracy is detected, meaning, yes, the system immediately flows to alert data stewards. The stewards then refine the knowledge source, updating or cleaning the data. But they can't just push it live. It must pass the ALM promotion gate, ensuring all security and quality checks are met. Only then does it deploy to production, refreshing the AI's brain. This diagram perfectly encapsulates that AI is an iterative, managed process, safeguarding accuracy, relevance, and trust continuously.